to the work that I have been doing the Topo-Mod project here in Barcelona together with Manuel Fernàndez, Montserrat Toné, and co-supervised by the Topo-Mod imperator, Claudio. And we also, as many of you might know, the African continent shows very interesting topographic features, which are strongly debated and discussed, especially in terms of their age and origin. And so the continent provides a very interesting laboratory to study the lithospheric structure and its relationship to the long wavelength topography. As we heard in the morning, if one wants to study topography or to better understand its evolution, crustal thickness is a very important parameter to know. But unfortunately, in Africa, knowledge of crustal thickness is very rare. And so our motivation in this project was to fill the data gap and to improve the knowledge on depth to MOHO and even to the LAB. And to do that, we are going to map the crustal and lithospheric thickness across the continent. And we are doing that by using a methodology that was actually presented in 2007 by Fuea and his colleagues. And this allows us to calculate the MOHO depth and LAB depth by combining geoid and elevation data together with the thermal analysis and the 1D approach, which is automatically fitting the observed geoid and elevation data. This model is assuming a local isostasy with the depth of compensation not at the core mantle boundary, but within the asthenosphere. And this model consists of 4 layers: seawater, crust, lithosphere, and asthenosphere. The density in the crust is considered to increase linearly with depth, and in the mantle it is considered to depend on the temperature. The crustal and lithospheric thickness is then calculated relative to a reference column, lithospheric reference column, and as I said, will fit then automatically geoid and elevation data. So the data come from the eTopo1 global relief model for topography and from the geoid model EGM 2008. These data were, of course, used, filtered, and truncated in order to avoid small frequency disturbations in the MOHO and LAB signal. Also, we collected a big compilation of information on crustal thickness in Africa, available from active and passive seismic experiments. And as you see in the figure, red will give the location of temporary networks or permanent stations, and the yellow ones are seismic data coming from active seismic experiment like reflection or refraction data. Also across the margins to have a better idea of the transition from the continent to the ocean. And this figure actually gives you, although we have more seismic data today available in Africa than before, you see it's still very local in some points and unequally distributed. So this is why we hope to fill the data gap with our model. And to do that, we had first to define a representative lithospheric column for Africa. And to that, we ran a couple of tests to define the best parameter setup. And the reference column depends very much on the crustal density, which is plotted here on the y-axis, and the value that sets the 0 level of geoid anomalies to geoid reference level. And here on the plot, you see each column represents an individual crustal thickness model fitting the data equally, the opposite. But we see that it needs pretty low density values. Here we are at 2.85, 2.75 to increase the fitting with the data. And this actually is just plotted until 2.75 here. If you would further decrease the crustal density to even unrealistic values, you would still observe a better fitting with the data in Africa. So we were thinking what's going on, and we decided to look what happens if we plot the observed against model data, and we found that a certain group of values is always within the same, is always among the outliers. And these values are located in the East African rift system. for example, in the Afar and Turkana depressions, in the Ethiopian plateau and rifts, and also in the Red Sea area. And so we found that we were comparing our model, of course, in a region where our methodology is critical, because we know we have rising plume beneath the lithosphere. There is lithospheric and crustal thinning observed, and the mantle temperatures and densities are everything else than normal. So also there's no, let's say, isostasy. So as a lot of data in Africa, seismic data, come from this region, we thought to run all the tests again without including the data from the East African rift system. And we found, of course, an increased fitting with the data, but also for more reasonable crustal density values. If we took now this point here for 2.8, let's say, gram per cubic meter average crustal density, we checked what happens if we compare, let's say, if we look at the difference between observed and modeled crustal thickness, and we found that there's an overall good agreement in the African plate, in the margins, even in the northern part, and in the Cap Verde Craton, in the Zimbabwe Craton, even in the Tanzania Craton, in the Arabian Peninsula, and here at the west coast in Cameroon. So how does the resulting crustal thickness and lithospheric thickness map look like? If we look at this map, we see that crustal thickness varies more or less from 28 kilometer in the margins to about 45 kilometer in the cratons, but also in some parts exceeds this thickness, and this is completely unrealistic values due to the fact that our methodology does not allow to calculate from very high elevations in these regions. So that's a complicated area. The same for the lithospheric thickness. But if we don't focus on these regions and go back to the crustal thickness and compare the distribution of cratonic areas with the occurrence of thick crust, let's say crust thicker than 35 kilometers, we see a good distribution of thick crust, agreement between distribution of thick crust and cratonic region. If we compare our results with existing crustal models, they look pretty different, but of course they show similarities, especially the very thick or the thicker crust in the southern part of Africa. And what is interesting also that they are very different for this part in Africa where no data is available. Here. So if we compare also the accuracy of these models, we found that all of these models actually have a good agreement with seismic observations from passive seismics, but for active seismic, it's pretty remarkably different, the accuracy. The lithospheric thickness, of course, the model we can compare with scenery studies or receiver functions locally, but better with regional or continental tomography models. Here, if we look at the comparison with Fischwig 2011, we see that overall the distribution of thick and cold lithosphere agrees well with what is shown in the model of Fischwig, but the absolute values are way lower, are lower in our case by at least 20 kilometers in the cratons. So our cratons are too thin. As we considering these weaknesses, we are actually trying to account for lateral change in properties like the contribution of sedimentary basins to the crustal density, and we also like to change the density of the lithosphere with terms of the different age and depletion. So yeah, the conclusions, as you have seen, we are presenting a very simple approach and using homogeneous density in the crust. But we observe certain problems in the East African rift system, and for example, that in general the lithosphere is too thin in the Cap Verde and the West African Craton. But the model shows a reasonable fitting with seismic MOHO data, and there is some characteristics in the model that encourage us to extrapolate depth to the MOHO into places in Africa where no data are available. Thank you.